Okay, here we have a coil turning inside a magnetic field, and this coil will produce a EMF or voltage. Now, if you had a circuit that was connected with a resistor, like here, then you would actually then get a current as well. So, we'll pause it. A good position there. Okay, you can see this is actually where the wire is cutting the field lines, the magnetic field lines, at 90 degrees, and there you actually get your greatest voltage. Okay, so you actually see the dial on the voltmeter here connected in parallel to that resistor will have the greatest voltage across it. Now, the direction of the EMF created, or the current in this case, you use your right-hand Flemings. Okay, so instead of it being FBI for your left hand, for your right hand, it will be the motion magnetic field current. Okay, so the motion in this case is this black arrow going this way. Okay, so that will be the direction that you should direct your thumb in your right hand. Then the blue one is your direction of the magnetic field. Okay, so that is your pointing finger, so you point it straight down. Okay, and then your other three fingers, okay, so the index and so on, then point this way, which is the direction of the current, the direction of the red arrow. Now, these things here are commutators, and there's a brush, okay, and there's a brush going on this thing here, keeping a constant connection so the wires don't get twisted up as they go around. And this is the thing driving it. So we'll let it go around another half circle. You see, as you get to here, the motion is actually in the direction of the field lines, and so there's actually no voltage or current produced. You can see it on the graph. So we just went from the maximum down there, and we're now about to head back up to the maximum again, where it starts crossing at 90 degrees. Now you can see the wire we're looking at originally is down here, and you can see that now the current has changed direction. Okay, it's now going this way instead of before, because your thumb is now pointing in the opposite direction. It's pointing this way. It's hard to show, going this way. Instead of up the top, it was going this way. If you increase the speed of rotation, so let's say we start right down, we have a low EMF induced. Okay, so in other words, a low current, because remember, V equals IR, the greater the V, the greater the I. If we increase the speed of rotation, then you increase that voltage. And there's another way of doing a constant connection. Now what happens here is as this thing spins around, the current in this coil will change direction. Okay, so at the top here, this one was going to the right, then at the bottom, it then goes to the left because the direction has changed. However, the current through here is now always going the same way because of the commutator. Okay, so this commutator makes this connection change from one side to the other, and then it always keeps the current going the one way. So this is DC, and then without that commutator, just with brushes, you have a AC waveform. Okay, so AC, DC. DC just means it has to keep going in one direction. It doesn't have to be constant value, it just has to keep going in one direction.